Hello students, my name is Shashank Shekhar. So we were on the chapter coordination compound. So if I talk about the previous class, so till now we have covered the nomenclature, right? In the first class we covered the Warner theory, which was the first theory that describes our coordination compound. Then in the second class we moved to the isomerism part, right? And in the Warner theory we have also seen the different entities that are present in the coordination compound, like our ligand, metal ion. Okay, coordination entity means the ligand and metal ion constitute the coordination entity. Then we have the counter ions on the outside, right? So these things we have covered in the first class. Then in the second class we have seen the isomerism, which was basically due to the spatial arrangement of the ligands around the central metal. Okay. Then we have seen what is nomenclature, means what are the rules for the nomenclature. We have discussed those. Now in the today's class, we will discuss about some valence bond theories. Okay. So basically, there are various bonding theories that are given to explain the coordination compound bonding. Okay. So for that, the first theory that was given was of course of Warner, but in Warner did not explain many things like you can say about the shape of the molecule, the magnetic properties and all. Okay, so for that we have introduced many theories later on, and the first one was after Warner was valence bond theory. So today we will basically start bonding in coordination compound, in which we will see valence bond theory, and with the help of valence bond theory we will try to explain these three type of complexes: octahedral, tetrahedral and square planar. Now after that we will see that how this theory is better in explaining the magnetic properties. Okay, but still this theory was also not complete to explain the whole of the, you can say, coordination compound, like the color and all. So for that we will see the limitations, and at last just we will give a glimpse to the hybridization type. So you must have seen the hybridization type initially also when we were studying chemical bonding and all. Okay, so first of all, bonding in coordination compound. So why does we need to make more theories? So there are three reasons. First of all, why do only certain elements possess the remarkable property of forming coordination compound? So you must have seen that only D block elements are capable of making the coordination compound. You will not see that any P block element like oxygen is capable of becoming the central atom and all. So we will see what is the reason behind it. Second, why the bond in the coordination compound have directional properties. Okay, so they have directional property, right? We have seen that they have a different isomer that is present for a single compound, which is for a single molecular formula, and that is only due to the different spatial arrangement. So we'll see why where does this directional property comes from. And third is about the magnetic properties. Okay, magnetic properties, and of course your optical properties. That is as a result of that is the result of the directional property of the bond. So we will see these three things. Try to explain these three things on the basis of the different theories that we will encounter just now. First, so if I talk about the theories, the first is valence bond theory. Second is CFT. Then we have ligand field theory, and at last we will have molecular orbital theory. Talking about class 12, so if we just limit ourselves to the syllabus, then we are only interested in valence bond theory and your crystal field theory and some of the ligand field theory. That's it. Okay, so we'll not move to molecular orbital theory regarding the coordination compound. Although you have seen the molecular orbital theory in the chemical bonding chapter of class 11, but that will be too complex for coordination compound. Okay, so when we move to coordination compound, that is not only diatomic but multiple atoms are present, and to correlate all of those and make a molecular orbital diagram of this is becoming very difficult. Okay, it becomes very difficult. So we'll stick to valence bond theory and crystal field theory and some of the ligand field theory. First of all, valence bond theory. So valence bond theory, what is valence bond theory? What do we do in valence bond theory? So we know that the outermost orbital of this metal ions that are involved in bonding in the case of your coordination compound are N-1D, NS-NP or NS-NP-ND. Okay, so these two cases can be possible. So what happens these orbitals, they kind of superimpose, okay? They kind of superimpose on one another and form a degenerate set of orbitals. What is degenerate set of orbitals? Means the orbitals that have the same energy. Okay, so you know that our suppose you are talking about 1s2. So I'm talking about 1s orbital. Then 1s orbital has the lowest energy. Then we have 2s. Then we have 2p, and in this way the order goes above. But in say hybridization, what happens? Two non-degenerate means two orbitals which have different energy, or two or more orbitals which have different energy. They just combine and form a set of degenerate orbitals, right? And this set of degenerate orbitals will determine that whether the complex that is being formed is octahedral, tetrahedral, or square planar. And the deciding factor is our parent orbitals, right? So we get a set of degenerate orbital, but the parent orbital is the one which decides that which you can say which geometry it will occupy. So these orbitals are allowed to overlap. Okay, the overlap with the ligand. Now after the formation, so once we get this degenerate orbital or the hybridized orbital, this hybridized orbital lobes, okay, so we will see that different shapes are possible, octahedral, tetrahedral, and the orbitals of this shape are available for bonding or overlapping with the ligand orbital. Okay, and the ligand orbital are the one which donate the pair of electrons for bonding. Is this clear? So if it is becoming complex for you, we will see it through a diagram that will make the picture more clear. So the points you should remember is that those orbitals do combine or overlap to form a set of degenerate orbitals. Okay, sorry, they you can say they do not overlap. You can say they merge together. Okay, they come together and form a set of degenerate orbitals called as hybridized orbital. Now this hybridized or degenerate orbital overlap with the orbital of the ligands, and the ligands are the one which are donating the set of electrons or the pair of electrons. Now if I talk about this say hybridization, suppose one s orbital and 3p orbital combined, then it will form sp3 hybridization and the shape will be tetrahedral. Now if you talk about sp3, then sp3 has 4 lobes. Okay, there are 4 lobes. So I'm talking about lobes. Suppose if we talk about p orbital, it has 2 lobes, this and this. So similarly, your sp3 has 4 lobes. Now 4 lobes are available to overlap with the 4 ligand orbitals, and hence the coordination number is 4. Clear? Similarly, if we talk about dsp2, so 1d, 1s and 2p. Now this should be very clear. If 4 orbitals are overlapping, then this will result in a degenerate set of 4 orbitals only. Means the initial and final number of orbitals will be same. So 4 orbitals are combining, they will result in 4 orbitals. But in this case, these 4 orbitals will be combined. They will not be far apart. Similarly, if you talk about sp3d, there are 1, 2, 3, 4, 5. So 5 will be the max, the number or the coordination number. If you talk about sp3d2, then 6 is the coordination number, and d2sp3 also has a 6 coordination number. Now, if I talk about sp3, sp3 is tetrahedral, dsp2 is square planar, sp3d is your trigonal bipyramidal, and sp3d2 or d2sp3 is an octahedral. So we have seen this. Okay, we have just we have encountered this in class 11th, all this hybridization type. You just have to invoke those concepts, and this will be easy to do. Now I'm telling you once again, this valence bond theory will not explain the picture. Okay, the whole picture will be explained about, means I cannot say the whole picture, but the 95% of the picture will be explained by the CFSC, and the rest of those, the remaining one, was completed by the molecular orbital. But they are not add upon, right? So I'm not saying that crystal field theory is incomplete, then we add some theories to this crystal field theory only and make the theory complete. No, that theory is completely dropped off, and a new theory is developed that is more capable of explaining the coordination compound. Okay. So, suppose we are taking a complex to explain this theory. Suppose we take the complex as CONH3 whole 6 3 plus, right? Now, what will happen? If you just try to calculate the oxidation number of cobalt here, then there are 6 NH3. But NH3 is a neutral molecule, ammonia. Okay, so the charge on the NH3 is 0, and hence its oxidation number is overall 0. but the coordination compound has an overall charge of 3 plus. So this charge must be of the cobalt. Okay, it must be arising due to cobalt. So we can say that cobalt is in the plus 3 oxidation state because it has a charge of plus 3. And why is it so? Because our ammonia is neutral. So the same thing is written here. The cobalt is in plus 3 oxidation state and has the electronic configuration of 3d6. So you must be aware about the position of this cobalt in the periodic table. So if I just try to count it from the left hand side, that is potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt. So it comes on the 9th number. So 9 electrons are available. Now out of this 9, 3 are removed because it is in plus 3 oxidation state. So 3 must be removed. That will result in 3d6. So now the electronic configuration of the cobalt 3 plus is 3d6. And what about the ligand? So as I have told you right now that NH3 is the ligand here, and ligand donate a pair of electrons. So this NH3, one NH3 will donate one pair of electrons. Similarly, 6 NH3 will donate 6 pair of electrons. What do you mean by pair here? Means 2 electrons by one NH3. In this way, right? So if you just look at the structure of NH3, I'm just drawing the octet structure. You will notice that NH3 has how many electrons left? 1, 2, okay? And 3, 4, 5 are just involved in bonding. So total of 2 electrons are there on nitrogen. Okay, now these 2 electrons are donated. Okay, these 2 electrons are donated on the metal ion. Okay, so this is the pair of electrons I'm talking about. Clear? Okay. Now, since 6 NH3 are present, so 6 pair of electrons can be donated from ammonia. Thus, the complex has octahedral geometry and is diamagnetic because of the absence of unpaired electron. So how is it so? So we'll see this. Okay, so this is sp. This is octahedral. So 2 cases can be possible. One is sp3d2 and second is d2sp3. So we'll look at the D configuration and decide which one is adoptable. Now in the formation of these complex, since the inner d orbital is used, so it is called as inner orbital complex or low spin complex or spin paired complex. So all 3 names are possible. So how it happens, we will see. So if I talk about simple D6, it looks like this. So D6, 5 orbitals, 1, 2, 3, 4, 5 and 6. So this is D6. Okay, this is the ground state. But as the ligand approach, the story changes. Okay, the story can change, may or may not change. So both cases can be possible. It is not always that they will pair up. Okay, or they will do a change in configuration. It is not always possible, right? It will totally depend upon the ligand. So this is the thing that is happening here. As I have told, so we have the orbital of CO3 plus, that is D6, and this is the ground state. Okay, this is the ground state. We have only vacant s orbital and p orbitals. Now, as soon as the ligand approaches to this CO3 plus, what happens is that these 3 orbitals, okay, if I just round it off, these 3 orbitals are only available for electrons and they pair up. Okay, this goes here and this goes here. This results in this kind of configuration. Now the remaining one, okay, so if you just pair them up, you will be left out with D2, so 2d orbitals and 1s and 3p. Now this 2d, 1s and 3p, they combine together. As I've told you, they combine together and form a set of degenerate orbital. So it is D2sp3. Okay. Now in this case, you can see that 2 inner d orbitals are involved. Okay, so it is possible. Suppose 4d orbital was also there. So suppose the pairing would have not taken place, then the hybridization would be in this way: S, P3 and D of this means 2d orbitals from the 4d set. Okay, so this is also possible, but since the ligand is the responsible one, so it just pair this up. So it has been paired here, and we are left with D2sp3. So if you say that our n-1 d orbital, s orbital and p orbital, these 3 types of orbital, okay, talking it once again, n-1 d orbital, s orbital, ns orbital and NP orbital. If these three types of orbital are involved in say hybridization, then it is called inner. Okay, inner. But if NS, NP, and ND are involved, then it is called outer. So this is the difference between inner and outer orbital complexes. Now this I am again telling you this inner and outer orbital complex will depend upon ligand and somewhat upon our metal ion. Okay, clear? Now what will happen in the next step? This ammonia molecule will donate the pair of electrons. So in the 6 ammonia molecules, the 6 pairs of electrons will donated 1, 2, 3, 4, 5, 6. Okay, so 6 pair of electrons are come from 6 NH3 molecules. And this is the final electronic configuration according to your valence bond theory. And it has formed an inner orbital or low spin complex or paired complex. Clear? Is everything clear? Okay. So this was an example of inner orbital complex. And now we will move to the next type of complex. So this is octahedral. Now suppose we take the same metal ion. Okay, we take the same metal ion. That is, if you just calculate the oxidation state here. So cobalt is X. 6 fluorines are there. Each has a charge of -1. And the overall charge on the coordination entity is -3. So this will result in +3. Okay. So here also the cobalt is in 3+ oxidation state. So it will have D6. Okay. It will have D6. Now this ligand, that their fluorine ligand, is not capable of pairing this electron. Okay. So it will not pair up this electron. It will remain as it is. Therefore, as a result of this, the s orbital, 4s orbital, and 4p, and your d orbital of fourth shell, and not the third shell, takes part in hybridization, and it results in a new set of orbitals, that is sp3d2. sp3d2. Now in this case, outer d orbital is involved, so it is called as outer orbital complex. Now some student asks us, how will decide that whether this compound is forming outer or inner? Okay, so I have told that this fluorine will do the thing and NH3 will just pair it up and fluorine will not pair it up. So how will decide it? So this thing was not explained by valence bond theory. It will be later on explained when we will study CFSC. Okay, from that CFSC you will be able to answer these questions. Okay, clear? Now, next. 6 p orbitals are available, and this will be filled up by the fluorine. See, one fluorine F minus. Okay, so this will donate a pair of electrons. Similarly, 6F will donate 6 pairs of electrons, and this will result in outer orbital complex, high spin complex, or spin free complex. Okay, so the two sets are inner orbital complexes. So they are mainly named as inner orbital complexes and outer orbital complexes. In inner orbital complexes, N-1D, NS, and NP. These three are involved. Whereas in outer orbital complex, NS, NP, and ND are involved. Is this clear? This is inner, this is outer. It is also called as high spin. Sorry, it is also called as low spin. This is high spin. It's spin paired and spin free. Is it clear? So this was about the two types of octahedral complexes. Now you will notice one thing in both of these complexes, that in the first case we have no unpaired set of electrons. But in these octahedral complexes, that is the outer one, so I'm not saying that it will always be the case. Okay, it will not. I'm not saying it will always be the case, but I'm just saying that see how the outer and inner orbital, means the ligand is changing the electronic configuration, and now in the outer orbital complexes we can see that we have unpaired set of electrons. Okay, so there can be a case of outer orbital complex that there is no free electrons, right, and free unpaired electrons, but in this case we have free unpaired electrons, and hence this will show magnetic properties. Okay, paramagnetic properties due to the presence of unpaired set of electrons. Okay, so this should be kept in mind right now. I will use this concept later on. Okay, Now we have studied the octahedral complex. Now we'll move to an example of tetrahedral complex. So for octahedral complex, so if you just try to draw the picture of octahedral complex look like this. So here are the 4 ligands. So if I talk about NH3, there are 4 ligands and 2 on this axial position, right? Now we have seen that sp3d2 hybridization will take place. So this will result in this kind of orbital. Okay. So the sp3d2 will look like this, or the d2sp3. Both will look like this. Here, here, like this, and one on the upside and one on the downside. Now this 4 will be on the same plane. Okay, this 4 will be on the same plane. Let me just make proper diagram of it. And then we have this one. Okay. So this 4 orbitals, I'm talking about this one. So this one, this one, this one are on the same plane. So let me draw a square out of it. So if you just connect these dots, so this is the 4 set of orbital on the plane, and these are up and down. Okay. So this is the kind of setup, and this is now called as sp3d2 or d2sp3. Now you can see very clearly that 6 pairs of lobes are there. 1, 2, 3, 4, 5 and 6. Now what will happen next? The ligand will come. So suppose NH3 ligand is coming. So I'm just drawing the single orbital of NH3 ligand. So they will, what happen? They will just overlap with this. Okay, they will overlap with this. Similarly, one more orbital will overlap with this. Now this can be either P, D or S depending upon the ligand. So I'm taking the example of suppose P orbital, right? So this will happen. Here, now this p orbital, which is of the ligand, will have a pair of electron that will be donated to this metal ion, or will be shared, not donated, it will be shared to the metal ion. So in this way, the bonding takes place in our octahedral complexes. Okay, for the case of valence bond theory. So is this picture clear to you? So this will completely explain the valence bond theory. Now these 6 orbitals, although I have just colored with them different pen, red and green, but they are having same energy. You shouldn't be confused about them. Now let us move to tetrahedral. So for that, I have taken the illustration of NiCl4 2 minus. Now if you just calculate the oxidation state of nickel here, so let us assume it is X. So 4 Cls with a 4 negative charge will be there. I'm directly writing it's -4, and overall charge on the complex is -2. That will result in +2 oxidation state of nickel. So this means that the nickel is in +2 oxidation state. Now if I just take the electronic configuration, so potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. So it comes on the 10th part. So there are 10 valence electrons that are present in nickel. Now 2 of them are removed. That will result in 3d8. So what is the oxidation? What is the electronic configuration of the Ni2 plus? That is 3d8. Now the question comes whether this Cl minus ligand is capable of pairing the electrons or not. Okay. So I'm telling you a thing here that should be remembered, that since we are talking about tetrahedral, and in tetrahedral we do not see pairing. Okay. So in tetrahedral we will never see pairing. If it is paired, then it is not tetrahedral. Clear? So I'm saying that suppose we are saying D8. Okay, so D8 will look like this. 1, 2, 3, 4, 5, 6, 7, 8. Now this 2 will not pair because this is a tetrahedral. Now which will be tetrahedral and which will not be tetrahedral, how we'll decide it? So we'll see it in the later on class. The next lecture will be very important. You will get the answer of each of these questions, right? So I will give you some exceptions, a set of rules that will decide the pairing and non-pairing. Okay, clear? Now, next is, what are we left with? S orbital, I would say 4s orbital and 4p. Now we have Cl. Okay, so this Cl will donate electrons. One Cl will donate one pair, so 6 Cls will donate 6 pairs of electrons. Now before the filling of electrons, this will just combine and form the degenerate state because hybridization is very important. Okay, so hybridization will take place. If I just draw the next level, 1, 2, 3, 4, 5, 6, 7, and 8. So they will just pair up and form sp3. 1, 2, 3, 4. Okay, and the electrons will be 1, 2, 3, 4, 5, 6. Each coming from one Cl. Cl, Cl, Cl. 6, 4 Cl are there, so 4 pairs of electrons. Okay. Similarly, for NiCO4, the same thing happens, but the thing here is that we will not see the say oxidation state. Okay, so there will be no change in oxidation state. It will be in zero oxidation state because CO is a neutral ligand. Okay, CO is a neutral ligand, so it will be in zero oxidation state. And since D10 is present, so D10 will be this. Okay, so this will be D10. No unpaired electron, so you don't have to worry about pairing and non-pairing. Of course, it will go to sp3. So is this clear? Okay. So as I have told, Ni2 plus is this. Now 4s and 4p, 3, 4p and 1 4s will combine to give sp3, and Cl will donate 4 pair of electrons, and this will complete your bonding. This will complete a bonding and result in tetrahedral. Now if I ask you how will tetrahedral look like, it's simple. Just draw the tetrahedral shape. One here, one here, and this is your tetrahedral shape. Okay. Now we have 4 set of orbital sp3. Now 4 ligands can just come and combine. Suppose p or instead of p orbitals, s orbitals are coming. Okay, so let me draw it with a different pen. Okay, so this will just do on head overlap. Now this is very important to note here that our hybridized orbital will always do head on head overlap and never side overlap. Means they will always form sigma bond and not the pi bond. So this is very important to notice. Pi bonds are only formed by pure orbitals and never by hybridized orbital. Clear? So this is very important. So this is sp3, and sp3 is always tetrahedral in shape. So how does tetrahedral will look like? Just imagine this is the pen. Okay, this is the pen. Okay, this pen is here, and now 4 legs. This is the one leg, and rest of the 3 legs comes like this. Okay, just a tripod. They forms a tripod on the downside. Clear? So this is a 3D picture, and the shape comes out to be tetrahedron. Okay, so we are done with the tetrahedral complexes. Next, let us move to square planar complexes. So the difference between square planar complexes and your tetrahedral complexes is that, so in square planar complexes, what happens is that our orbitals do paired. Okay, the electrons in the orbitals get paired up. So NiCN4, if you just calculate the oxidation state, it will be again +2. And +2 oxidation state means D8 configuration. Now what will happen in case of nickel? The two unpaired electrons will get paired up because of the presence of a different ligand, that is cyanide. So this cyanide will just, what will it do? It will just pair up this electrons and it will result in zero unpaired electrons. Now we have one d orbital, okay, then we have one s orbital and two p orbitals. So dsp2, okay, dsp2, 4 orbitals will be involved and hence it will form square planar complex. So the complex is diamagnetic as evident from the absence of unpaired electrons. So if we talk about the previous one, that is our NiCl4 2-, it has two unpaired electrons and hence it is, you can say hence it is paramagnetic in nature. But if I talk about this complex, that is NiCN4 2-, it has no unpaired electrons. So it is diamagnetic in nature. Okay, clear? So this is the electronic configuration. So initially we have seen is D8. Now hybridization will take place, and for that pairing of electron will take place. So these orbitals will be left out. Okay, so D, S and 2p orbitals. So dsp2 comes and form this kind of hybridized orbital, 4 sets of hybridized orbitals. Now 4 CNs are there. Each CN will donate one paired electron, one pair of electron. So 4 pair of electrons will be present. That is total of 8 electrons. Clear? Now, as I've told you, we have seen this in octahedral complex. We have high spin and low spin, but both of those results in octahedral only. But in the case of 4 orbitals, we have two cases. If it is high spin, then it will be tetrahedral. If it is low spin, then it will be square planar complex. Means shape will change according to the high spin and low spin. Clear? You can also say it as inner orbital and outer orbital. So inner orbital complexes of 4 orbitals will form, or 4 lobes will form the square planar, and the outer orbital complex of 4 lobes will form tetrahedral. So again, if I draw the shape of the dsp2, it will look like this. One here, one here, one here, and one here. If I just join all of these with the help of dotted lines, so they look like this. Now just attach it with them or overlap it with them, the ligands of the orbitals of the ligand. Okay, so this is the final structure. Now this again, I'm saying this p orbital is coming from ligands and it can be s orbital also. It will totally depend upon the nature of the ligand, what type of ligand we are taking. Okay, clear. Now we'll talk about the magnetic properties. We have seen just now that different cases are possible and different ligands are giving different sets of pairing and non-pairing. Now this pairing and non-pairing is totally dependent upon the ligand. Okay, it's totally dependent upon the ligand. But for some cases, we can see that never the pairing will never happen. So D3 case. So if we have D3, the pairing does not take place. So the example are Ti3 plus. Okay, D3 is Cr3 plus, and for D2 also pairing will not happen. And D1 is alone, so we don't have to worry. So if we have D3, D2, and D1, and we have the octahedral complex. So listen it properly. So if we have D3, D2, and D1, and we have the octahedral complex, then pairing will not happen. Okay, pairing will not take place. Clear? So some points I'm telling it right now. I will just sum them up at last. Okay, so there will be many points, but 10 points will be enough to decide. Okay, to decide whether it will form inner and outer. Okay, so that will be disclosed tomorrow. Now, in case of octahedral, as I've told you, in case of octahedral, if it is D1, D2, or D3, it will always form high spin. Okay, I will not say if it will also form high spin. It will never pair up. So the maximum number of electrons will be the maximum number of unpaired electrons. So if it is D1, then unpaired electron is D1. If it is D2, then unpaired electron is D2. And if it is D3, unpaired electron is D3. In case of octahedral complex, pairing will not take place. Clear? But in case of tetrahedral, the case is not the same. After that, if we just keep on adding electrons, so if you have more than 3 electrons, so in that case, the pairing and non-pairing changes. Okay. So in some cases, we will see that 2 unpaired. So if we take D4, then we'll see that sometimes we have, so if you just draw it, D4, so D4 will look like this. 1, 2, 3, 4. So some will have 4 unpaired electrons and some will have 2 unpaired electrons because they pair up. So that will depend upon ligand and on the metal ion. Similarly, for D5, the pairing can take place. For D6 also pairing can take place and it cannot take place. Either way is possible. Now, the magnetic data agrees with maximum spin pairing in many cases, especially with coordination compound D6. What does this mean? That the magnetic data agree with maximum, so in maximum cases spin pairing take place. So this maximum word, although this is explained by VBT, but this is not full enough. So when I say it maximum, so in the exam, your maximum is not 100%. It can be 80, it can be 70, it can be 90, but it is not 100%. And for exam point of view, you should have the 100% view that which one is pairing and which one is not pairing. So we'll see this, okay? So it is said that if it is D6, then in maximum case, we see that there is a kind of pairing. Clear? But in the case of D4 and D5, there are complications. Suppose for MnCN6 whole 3 minus has magnetic moment of 2 paired electrons. But in case if it is replaced by Cl, we have 4 unpaired electrons. Means the pairing has taken place from Cn to Cl. Okay, clear? Now, similarly, if I talk about FeCN6 whole 3 minus, it has a magnetic moment of single unpaired electron. Okay, so one unpaired electron is present. But in case of FeF6 3 minus, so if you just change the ligand from Cn to F6, then it has a paramagnetic moment of 5 unpaired electron. Okay, paramagnetic moment of 5 unpaired electrons. Clear? So these are the complications. So if you are just trying to solve the question from this data, just remember this data. Okay, so we'll just try to make a more clear picture when we'll move to this crystal field theory or the CFT or the CFSC. Now this apparent anomaly explained by the valence bond series in terms of inner orbital complex and outer orbital complex. So they just say that this is inner orbital, this is outer orbital, this is again inner orbital, this is again outer orbital. So they're just saying it. They do not have any valid reason behind it for the case of valence bond theory. So this and this, that is MnCN6 whole 3 minus, FeCN6 whole 3 minus, and CO C2O4 3 minus. They all are inner orbital complexes and involves D2sp3 hybridization. The former two complexes are paramagnetic and the latter are dimagnetic. Okay. On the other hand, if we talk about MnCl6 3 minus, FeCl6 3 minus, and COF6 3 minus, they all are outer orbital complexes involving sp3d2. So they all are outer orbital complexes and are paramagnetic corresponding to 4, 5, and 4. 4 is 5 and 4. Now, what we will do is we'll try to do the thing. Okay. So first of all, let us take these examples and try to draw the electronic configuration. First is MnCN6 and 3 minus. So in this case, Mn is having plus 3 oxidation state, and that will result in what will be the electronic configuration? Potassium, calcium, scandium, titanium, vanadium, chromium, manganese. D7, 7 minus 3, D5. Okay, D5. So the initial configuration of Mn3 plus will be 1, 2, 3, 4, and 5. Left will be S and P. So this is 3D, 4S, and 4P. Now it is said that this is forming a inner orbital complex. So what will happen? Pairing will take place. So if we just pair them up, five. So we are left with one unpaired electron. And what will happen? Simultaneously, they will just do the hybridization along with two d orbitals. This is not drawing it whole. So these two d orbitals will just combine and form the set of D2sp3. 1, 2, 3, 4, 5. This is D2sp3. Now six CNs are there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and one more, 11, 12. So these all are coming from the CN. Okay. If I just draw it with a different pen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 6 CN, 12 electrons. Okay. So this is the final structure. Okay. Next, let us draw it for say, let us draw it for FeCN6 3 minus. Okay, FeCN6 3 minus. So I will draw it. Say, just try to draw it by yourself. Okay. Okay. FeCN6 whole 3 minus. This will be good. Okay. Now, if I just tell you the oxidation state, then it would be potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron. Iron is D8. So after 3 electrons are removed, it will be D5. Okay, it will be D5. Now D5 is in this way. Okay, D5 is in this way. This is 4s, this is 4p, this is 3d. Now it is said that is the inner orbital complex. So pairing will take place again. One, two, three, four, 5, and rest will be as it is. Now after this, 2 orbitals are left, and they will just form the set of what? Your SD2sp3. Okay. Here, now Cn will donate the pair of electrons, 2 electrons from 6. Okay. So this will be your FeCN6, and it will be D2sp3. Now here you can see that it is having one unpaired electron. In this we have one unpaired electrons. Okay. Potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, D8 minus 3, D5. What about manganese? Potassium, calcium, scandium, titanium, vanadium, chromium, manganese is 7. 7 minus 3, it is 4. So it is D4. Okay, so this is the mistake I have done here. Now one thing will happen here. We will have an empty d orbital. Okay, so this will not be participating in electron filling. Okay, so this one I have done wrong, so I have just corrected it right now. because only 4 electrons are there. Okay. Now next, CO C2O4 3 minus. Okay, so you tried by yourself. This one you tried by yourself. Okay, I'm doing. Suppose I am doing it for F6 3 minus. Fe F6 and 3 minus. How will happen? How it will happen? Again, it is D5 here, right? Because it is in +3 oxidation state. Okay. So what will happen? This will be electronic configuration, but since it is the outer one, so there will be no pairing. So it is clearly written here, right? So this is the outer orbital complex, right? So how many unpaired electrons are there? 5 unpaired electrons. Okay, 5 unpaired electrons. Then we have sp3 and d2. I'm not drawing the rest of the 3 orbitals of d. I am only drawing the 2 which is required for hybridization. So this all will take part in hybridization and will form this thing. So this is 1, 2, 3, 4, 5. This one is what? 3D, and this is sp3d2. Okay, clear? So this will form a outer orbital. So this is the formation of outer orbital complexes. Now if I ask you what is the number of unpaired electron? 5. So more is the number of unpaired electron, more stronger properties of magnetism are shown by the complex. Clear? Next is one formula has been not taught here. I think we will encounter this formula in the CFSC or the CFT theory. Okay, so that is just finding the magnetic moment. So formula is very simple. I'm just telling it right now. N into n plus 1, where n is what? Number of unpaired electrons. Suppose I'm trying to find it for this one. So 5 into 5 plus 1 root under. Similarly, just try to find it for COF6 3 minus and MnCl6 3 minus. So this was all about your valence bond theory. So they have just explained all of this, magnetic properties and all. But there are some limitations again. What are those limitations? Now, first of all, it assumes many things, right? There are number of assumptions that they just combine and form this hybrid set of orbitals. There is no reason behind it why it is doing so. First. Second is, it does not give a quantitative interpretation of magnetic data. So you will see this CFS, this formula in the CFSC part and not in this, that root under n into n plus 1. So they are saying that there are number of unpaired electrons. But on what basis they are saying it, right? That this will be stronger and this will be weaker. That is not completely explained. They have just told they have unpaired electrons, so they will show paramagnetic properties, but that is not quantified. Third is, no color properties are being explained. So when you will see the coordination compound in real, they are very colorful. Okay, they are very colorful, starting from red, orange, green, and various colors are being shown. Now there must be a reason for the color exhibition, because your simple metal ion have a different color, but after forming coordination compound, it forms a very different color. Now this color phenomena is not explained by this theory. There is no explanation of that. Next is, it does not give a quantitative interpretation of the thermodynamic or kinetic stability. So they are neither talking about the kinetic stability. So if you just take a coordination compound, there is a type of variability in their stability. Means kinetic stability means whether it will react or not. Thermodynamic means whether it is stable or not under heat. Okay, so these are two different things. So you should always keep this in mind, that kinetic, if something is reactive, it does not always say that it is not stable. So it can be possible that something is stable and still it is reactive. Okay, so it completely depends upon the structure. So kinetic stability and thermodynamic stability are not explained by this valence bond theory. and it does not explain when it will form tetrahedral and octahedral, tetrahedral and square planar. Okay, because it is not explaining when it will pair up and when it will not pair up. Similarly, it does not distinguish between a weak and strong ligand. Same thing is written here. So if it is weak, it will just not pair it up. If it is strong, it will pair it up. Okay. And also in the octahedral complex, it will not say that whether it will form inner or outer, when will the case of inner and when will is the case of outer. They are completely saying it on the basis of experimental data. So if it is seen that your paramagnetic behavior is shown, so they are saying it, okay, so this is the thing. Okay, you will get my point. So they are saying it on the basis of the experimental data, and no theory is there to explain that whether it is weak, strong, and why the pairing is taking place and why the pairing is not taking place. Next, this is the set of hybridization. So why have I put this picture? This is very important. Okay. So I am saying that, okay, so trigonal pyramidal has a hybridization of dsp3. Now d orbitals are all different. Okay, d orbitals are all different. Yeah. But the difference here is that if I talk about dsp3 and dsp2, then S orbitals are same, or s orbitals are same. Only one type of s orbital is present. In case of p orbitals also, all p orbitals have same shape, but d orbitals have not the same shape. Some are having double dumbbell, some are having along the axis, some are between the axis. So they all are different, right? Clear? So for this reason, what will happen? We will see that, okay, we will see that different kind of orbital will take part in different kind of shape. So if we have a different shape, we have a different orbital. So if I talk about square planar, then the d orbital that is being involved here is dx square minus y square. This is written wrong. This is not correct. Where in case of trigonal pyramidal, dz square is involved. Okay. Similarly, for octahedral, dz square and dx square minus y square is involved, both for inner and outer. Clear? If I try to just rationalize it, so for rationalizing it, just think of the square planar complex. Okay, so it is having all the d orbitals, so all the lobes on the same plane, right? Like this and like this. Okay, so 4 orbitals are there. Now, if you just compare it with the dx square minus y square, they are also along the axes. Okay, and they are also on the same plane. So due to that reason, dx square minus y square takes part in the formation of square planar complex. Whereas in case of trigonal pyramidal, this is not the case. Okay, so if in case of trigonal pyramidal, it looks like this. So we have this thing, this here, and this here. So this is the shape of trigonal bipyramidal. Now, the d orbital that is involved, it is dz square, and the maximum property of dz square is along this orbital, which is on the equatorial part, right? So you can try to just rationalize it in this way. Clear? So with this, I end my lecture. So we have seen valence bond theory whole, and now in the next class we will move to a much better theory, that is the crystal field theory. For now we end this class. Okay, thank you.